Hello, my dear students. How are you? I am Professor H.R. Sani. I hope you must be enjoying my lectures. My today's lecture is for the students of 10th class and the topic is Ohm's Law. Now, first we have the statement of Ohm's Law. Ohm's law states that the physical conditions of a conductor, like its dimensions and temperature, etc., remaining the same, the current flowing through it is directly proportional to the potential difference applied across its ends. For example, if this is a conductor, we apply a potential difference V across its ends so that a current I flows through it. Then, according to Ohm's law, I is directly proportional to V, or V directly proportional to I, provided the physical conditions like dimension means its length, its area of cross section, then of course temperature and pressure, etc., remaining the same, then I proportional to V, or V proportional to I, or V equal to some constant, and that constant is R, I into R, where R is the constant of proportionality and is known as the resistance of the given conductor. Its value depends upon number 1, nature of the conductor, number 2, length of the conductor, number 3, area of cross section of the conductor, number 4, its temperature. And physically, the resistance of a conductor is its property due to which it opposes the flow of charge, that is the flow of current through it. Now, from this equation 1, we get R equal to V over I. Therefore, the resistance of a conductor is defined as the ratio of the potential difference applied across its ends to the current flowing through it. The SI unit of resistance is ohm, and its symbol is capital omega. Now, if V equal to 1 volt, I equal to 1 ampere, then R equal to 1 ohm, that is 1 ohm equal to 1 volt over 1 ampere. So therefore, the resistance of a conductor is said to be 1 ohm if a current of 1 ampere flows through it when a potential difference of 1 volt is applied across its ends. Now, as V directly proportional to I, and whenever two quantities are directly proportional to each other, the graph between them is a straight line passing through the origin. Therefore, if we plot a graph by taking potential difference V along x-axis and current along y-axis, the graph obtained will be a straight line like this passing through the origin O. So this is the shape of the graph. Now, a conductor which obeys Ohm's law is called ohmic conductor or ohmic resistance, and this relation V proportional to I is of course true for the ohmic conductors, and for the ohmic conductors the graph between V and I is a straight line passing through the origin as shown in the figure. But the conductors which do not obey Ohm's law, they are called non-ohmic or non-linear conductors, and in their case the graph between V and I is not a straight line but it is a curve. Now, factors on which the resistance of a conductor depends. Factors on which the resistance of a conductor depends. On which the resistance of a conductor depends. The resistance of a conductor depends. Number 1, length. The resistance of a conductor is directly proportional to its length, that is R proportional to L. Number 2, the resistance of a conductor is inversely proportional to its area cross section, that is small a. And it also depends upon the nature of the material of the conductor and the temperature of the conductor. Now if I combine these two factors, I get R proportional to L by A, or R equal to some constant, and that constant here is rho into L by A, where rho is the constant of proportionality and is known as the specific resistance or resistivity of the conductor. Its value depends upon the nature of the material of the conductor, and its value depends upon the nature of the material of the conductor. That is why the resistance of a conductor also depends upon the nature of the material of the conductor. I call this as equation number 1. Now definition of specific resistance or resistivity of a conductor. If L equal to 1 meter, unit length 1 meter, A equal to 1 meter square, then from equation 1, R equal to rho into L by A implies R equal to rho into 1 by 1, that is rho equal to R. Therefore, the specific resistance or resistivity of a conductor is numerically equal to its radius if the length of the conductor is 1 meter and area of cross section is 1 meter square. So therefore we can define resistivity or specific resistance of a conductor as follows. The resistivity or specific resistance of a conductor is the resistance made of that material, that means material of the given conductor, whose length is 1 meter and area of cross section is also 1 meter. Now a conductor whose length is 1 meter and area of cross section is 1 meter square is called a meter cube. That means it is a cube whose each side is equal to 1 meter, like this. This is a cube. Its each side is 1 meter. Now this is the area of cross section. Now this area is 1 meter into 1 meter, that is 1 meter square, and this is the length, that is 1 meter, and therefore specific resistance or resistivity of a conductor may be defined as the resistance of 1 meter cube of the conductor made of that material. So that is the definition of specific resistance or resistivity of a conductor. Now units of specific resistance or resistivity. From the equation R equal to rho into L by A, we get rho equal to R into A by L. Therefore units of R, rho equal to units of R into units of A over units of L. Therefore SI units of specific resistance or resistivity are ohm meter square over meter, that is ohm meter. So these are the units of specific resistance or resistivity. Now as resistance of a conductor depends upon rho, L and A, therefore resistivity depends upon R, but it does not depend upon A and L. It does not depend upon the length of the conductor. It does not depend upon the area of cross section. It depends upon the nature of the material of the conductor. That means its value is different for different material. For example, if we have a copper wire of certain length and another copper wire of length double the of length double than that of the first, and area of cross section say 3 times than that of the first, then the resistances of these two wires will be different, but their specific resistances or resistivity will be the same, because the specific resistance or resistivity does not depend upon the length, it depends only on the nature of the material of the conductor, but it depends upon the temperature also. Therefore, with the increase in temperature, the resistance and also the resistivity of the conductor increases. Now, depending upon the resistance offered by conductors, we can classify the different materials into conductors, insulators, and semiconductors. Conductors are those which offer very low resistance, that is, which allow the charge to pass through them easily. They are known as conductor. For example, all metals are conductors of electricity, rather very good conductors of electricity. On the other hand, the materials which do not allow the charge to pass through them, that is, they do not allow the current to pass through them, they are called insulators. For example, plastic, wood, glass, etc. are insulators. And there is a third category of materials which are called semiconductors. The materials whose conductivity lies in between conductors and insulators are called semiconductors. And two typical examples of semiconductors are germanium and silicon. So that is all in today's lecture. I hope you must have enjoyed it. Please like, share, and subscribe to my channel. Thank you very much. Have a nice time.